So what we're doing in these examples is we are finding the radii of convergence for these power series. And one thing we learned earlier is that a power series is always going to converge at its center. Every power series will converge at its center. The center of our power series in example 3 is 0. So let's take a look at what's happening when x is equal to 0. When x is equal to 0, we have the sum from n is equal to 0 to infinity of n factorial 0 to the n. Let's just look at the first couple of terms of that. When n is equal to 0, we have 0 factorial 0 to the 0. When n is equal to 1, we have 1 factorial 0 to the 1. When n is equal to 2, we have 2 factorial 0 to the 2, dot, dot, dot. So 0 to the 1 is 0, 0 to the 2 is 0. All of these other dot, dot, dot terms are going to 0, but 0 to the 0 is 1, and 0 factorial is also 1. So this is 1 times 1, which is just 1. And then a bunch of other zeros are being added to that. So we know what's happening at the center of this interval. We know that it is converging. Generally speaking, we won't typically look at the center because we always know that the power series is going to converge at its center. So now that we know that, so typically what we'll do is we'll say, well, what if we have x values that are not equal to 0? We know what's happening when x is 0. Let's see what's happening when x is not 0. When x is not 0, I'm going to take this entire expression that's on the inside of the power series, and I'm going to call it, we could call it a sub n, we could call it u sub n. I'm going to call it u sub n. I don't want it to be confused with the a sub n that we used before in this lesson. I'm calling that. And the reason that I'm calling that everything on the inside of the series that is because now I want to use the ratio test. So if I'm going to be using the ratio test, I need to be looking at the limit as n goes to infinity of the absolute value of u sub n plus 1 over u sub n. So just really quickly, summary of series. I am using the ratio test here, so I have let everything on I just called that all u sub n, right? And now I'm going to be looking at this limit here to see if it's less than 1 or greater than 1 or what, to see what conclusion we can make about the convergence of that series when x is not 0, because we already know what's happening when that series when x is 0, which I just noticed one thing I did, the ratio test has absolute values here, so make sure that you do have that. Is that, let's see, lesson 17. I'm just going back to the notes. Yeah, notice in all the examples in the notes, I have absolute values. And if I don't have absolute value, it's because I don't need it. If we only have expressions that only have n in them, then we don't need them. But the ratio test does have these absolute value bars in here. So that's why I have the absolute value bars written on this. So let's continue in this example. So we're looking at the limit as n approaches infinity of the absolute value of, I'm replacing n with n plus 1. So I have n plus 1 factorial x to the n plus 1. This is u sub n plus 1. And I'm going to divide this by u sub n. I'm going to go further and simplify this. N plus 1 factorial is n plus 1 times n factorial. X to the n is x to the n plus 1 is x to the n times x. And I'll leave the n factorial and the x to the n in the denominator so that I can see that the x to the n and the n factorial will cancel. And that leaves us with the limit as n goes to infinity of the absolute value of n plus 1 x. Well, really just the absolute value of n plus 1 times x. Now, we're taking this limit as n goes to infinity. N is the only thing that's going to change. So this x right here we can think of as a constant in terms of the limit, because the x is not going to be affected by that limit. So I'm going to pull out the x, and I am pulling out an absolute value of x. And we have the limit as n goes to infinity of just n plus 1. And this limit definitely equals infinity. So because this limit is equal to infinity, think about what the conclusion of the ratio test says. I'll go back to our summary of series. The conclusion of the ratio test says that if that limit is equal to positive or negative infinity, then the series will diverge. So what that tells us is that, there we go. What that tells us is that our series diverges when x is not equal to 0. Another way to write that is it diverges if the absolute value of x is greater than 0. So we knew that when x is equal to 0, that the series converges. So if I'm making a number line, we had tested at x is equal to 0 and we got convergence. But anywhere where the absolute value of x is bigger than 0, anywhere over here that I'm shading in purple, we have divergence. So this is the first case. I'm going to take the shading off just because I don't want that to be confused with the radius of convergence. So in this case here, our radius of convergence is simply 0. I want to be clear, it is not 0 because it converges at 0, it is 0 because it only converges at a single point. Power series always converge at their center. This only converges at its center. If its center would have been 2, the radius of convergence still would just be 0 because it would have only converged at a single point at 2. Let's look at example 4. We're going to approach this the same way, where we start off and we say the center of this power series is 2. We know that power series always converge at their center. And so let's see what's happening when x is not equal to 2. I'm again going to let the expression on the inside of the sum be my u sub n. You don't necessarily have to call it that, but I just do that so that I have something to write when I set up my ratio test, which I'm looking at u sub n plus 1 over u sub n, that limit inside the absolute value. So we have the limit as n approaches infinity of 3 to the x minus 2 to the n plus 1 divided by 3, I said to the, but 3 multiplied by x minus 2 to the n. And we're going to do the same thing we've always done with these exponents and break them up. We do have some things that can cancel in here. The 3's can cancel. In the numerator, we have x minus 2 to the n with an extra x minus 2. And in the denominator, we just have x minus 2 to the n. And so we are just left with the limit as n approaches infinity of the absolute value of x minus 2. So these x minus 2's here canceled. X minus 2 to the n here canceled. So this is what we are left with. The conclusion of the ratio test tells us that this series will converge when this absolute value is less than 1. That less than 1, that is the condition for convergence. And I'm getting that, going back to our summary of series, I'm getting that from right here. When will the series converge for the ratio test? When that limit is less than 1. So I'm setting that, let me just go a step further, by the way. This limit is just equal to the absolute value of x minus 2. That limit, because there's no n on the inside of that. So this entire x minus 2 can be thought of as a constant in terms of the limit, because no matter what n is going to, x minus 2 is not going to change. So solving this absolute value inequality, we can the absolute value of x minus 2 being less than 1 is equivalent to saying that negative 1 is less than x minus 2 is less than 1. This goes back to 171, where you learned how to solve absolute value inequalities. And so, in fact, I don't even have to, we'll go into this part later. We can ignore that for now. But we do know that this series converges when the absolute value of x minus 2 is less than or equal to 1. So we knew it converged at 2, and we're now seeing that we can move up to 1 unit away from 2 to get the to still have convergence. So in other words, the radius of convergence for this series looks like it definitely converges at its center of 2. And we could move possibly up to 1 unit to the right and possibly up to 1 unit to the left. We have not talked about what's happening at the endpoints. I just know that it converges at 2 and definitely up to 3 and up to 1. We have not talked about what's happening at 1 and 3. We will look at those. We will look at that in separate examples. All we're doing in this example is finding the radius of convergence. How long is this interval? How far to the right could I go? That distance there. More specifically, how far to the right from the center of the power series could I go? Example 5, we're going to set this up the same way. This series is centered at 0. So I'm going to start off by looking at the limit as n goes to infinity of the absolute value of, first I'm plugging in n plus 1, so I have negative 1 to the n plus 1 over 2, replace the n with n plus 1. Do the same thing in the denominator, replace the n with n plus 1. And then we're going to divide this by u sub n. So I'm just going to go ahead and multiply by the reciprocal of the original expression u sub n. So I have flipped what was on the inside of the series to give me this. I'm going to do some simplifying in here because we have, I'll break up the negative 1 to the n plus 1, which is just the negative 1 to the n times the negative 1. This exponent here, there's 2 times the quantity n plus 1, that's equal to 2n plus 3. Keep in mind that's the same thing down there. That's equal to 2n plus 3. So we have x to the 2n plus 3 in that numerator, and then we're also multiplying that by a 2n plus 1 factorial. In the denominator, we have a 2n plus 3 factorial, simplifying that expression on the inside of the parentheses, a negative 1 to the n, and an x to the 2n plus 1. Some things can cancel. You can cancel out that negative 1 to the n. You can get rid of this negative 1 as well because the absolute value of negative 1 is equal to 1. So that's not going to be changing anything. So we have the limit as n approaches infinity of the absolute value of, I'm going to break up the x to the 2n plus 3. That's x to the 2n plus 1 times x squared. And the reason that I'm writing it like that is so that I can cancel it with that x to the 2n plus 1 that's in the bottom. I'm going to leave this 2n plus 1 factorial right there. This 2n plus 3 factorial, I'm going to start breaking it apart by 2n plus 3 times 2n plus 2. And I'll stop at 2n plus 1 factorial. And then that x to the 2n plus 1 is still in the denominator. And that is the reason why I rewrote the one in the numerator so that we can cancel those. I'm also going to go ahead and cancel these 2n plus 1 factorials. And so I am left with the limit as n approaches infinity of the absolute value of x squared over 2n plus 3 multiplied by 2n plus 2. Now we've seen examples before where we have talked about how the x in the numerator does not affect the limit because there's no n in there. X squared is always greater than 0, so I don't even need to pull it out inside the absolute value. I can just pull an x squared out in front. And I'm just left with the limit of 1 over, notice I'm not putting absolute values here. You could, but you don't have to, because these 2n plus 3 and 2n plus 2 on the bottom is always going to be positive, since we know that n is greater than 0. So this limit goes to 0. Well, we know that limit goes to 0 because the degree of the denominator is bigger. So the bottom goes to infinity, which takes the whole thing to 0. So we know that this limit goes to 0, and 0 is less than 1. So the ratio test tells us that this series converges. And it converged for any x. It does not matter what x is. No matter what x is, this limit is going to go to 0. It's not like in the previous example where it was converging. Remember, the condition for convergence is that the limit is less than 1. In the previous example, the limit is only less than 1 when the absolute value of x minus 2 is less than 1, which gave us a radius of convergence of 1. But in this case, the limit is always less than 1. It does not matter what x is, so x could be anything. Because x can be anything, the radius of convergence is all real numbers. The entire number line would be shaded.